Alright guys, getting into part 1 of section 9.3. There's going to be 2 parts to this one. We're going to break this up over 2 lessons, but we're kind of switching gears now into the area of sequences and series. Remember, chapter 9 is a bit of a grouping of content under the umbrella of discrete math. And so this is just sort of another area that falls under that category. You may or may not have seen some sequences and series in the past. This topic has really bounced around under different levels of math. When I taught Algebra 1 15 years ago, we taught algebraic sequences and series, and so that was a long time ago, and then it sort of moved into Algebra 2, and then for a while it went down into geometry, and then it went to pre-calculus, and so you may or may not have seen some of this in the past, but I'm going to, of course, treat it like you have not seen any of this before. So let me start getting into this. As always, guys, I always like to identify page numbers where you can find more information if you ever need to look at more examples or definitions or anything like that. So there's a couple different ways to define a sequence of numbers. And remember, a sequence is just like a pattern of numbers. There's different types of sequences, which we're going to talk about, but it just comes down to some type of a pattern of numbers. So there's kind of 2 ways to do this. One is to identify it explicitly. Another way is to identify it recursively. And so the first thing we're going to talk about is explicit definition of a sequence. So and I actually like this much more than the recursive way of looking at it, and I'll show you why in just a minute here. So this says find the first 3 terms and the 20th term of a sequence. So this is just the title that we're giving to it. A sub k is just the title of the sequence, where A sub k is defined as 3k minus 4. So let me explain real quick what these things mean. This is the rule for identifying any term within the sequence. K represents the term number. So if I want the first term in the sequence, I just plug in a 1 for k. If I want the second term in the sequence, plug in a 2 for k, right? On and on and on. This is the result, right? So super, super important connection between these guys. As I plug numbers in for k as the term number, the result that I get is a of k. So for example, if I want the first term in the sequence, I would identify that as a sub 1, right? In other words, I'm going to plug in a 1 for k to get my result here. So if I plugged in a 1 for k, it's going to look like this. And so what do we get from that? Obviously 3 minus 4 is negative 1. So we would look at this and we would say, okay, the first term of the sequence has a value of negative 1. Obviously very similar to y equals mx plus b, right? Where x was like the input, the number that you put in went in for x, and the result, the output, was the y value. Exact same idea with this. It's just basically different letters, right? But otherwise it's really this exact same idea is what we're doing on this. So anyway, let me keep going on this. So they wanted the first 3 terms. So there's the first term. Second term is where we would plug in a 2 for k. So if I plug in a 2 for k, so 6 minus 4 is 2. And the third term, if we plug in a 3 for k, so 9 minus 4 is 5. All right. If you continued on with this pattern, you would notice that they are steadily increasing by 3 units every time. In other words, I already know the 4th term is going to be 8. I know the 5th term is going to be 11, and I could keep adding 3 every time to get the next term in the sequence. How do I know that? Well, one is obviously by looking at the pattern here. But to be honest, I already knew that in advance. As I look at this, if I consider this a linear sequence, which it is, right, like a line, mx plus b, my slope, or my rate of change, tells me what I am increasing by, right? I am increasing by positive 3 with every single term in the sequence, right? So obviously a very strong connection there. What if I wanted the 20th term? And here's the reason why I really like the explicit rules way more than the recursive rules, and you'll see that here in just a minute. So if I want the explicit, or sorry, the 20th term within the sequence, I can do the exact same thing I did here, and I can simply plug in a 20 for k. So if I want the 20th term, I would write it like this. So 3 times 20 is 60, minus 4 would be 56. All right. So let me give you one more item here, and then we'll talk recursive rules. What if I'm given the pattern, and I am asked to write the explicit rule for the sequence? This, in my opinion, is one of the hardest things potentially that there is to do for a sequence. And the reason for that is, as I look at this, it can fit a formula, but it might not. So for example, I don't know if this is a linear pattern or an exponential pattern. Maybe it's arithmetic, maybe it's geometric. It's sometimes there is no formula for these, and you just have to figure it out. Like, you just have to figure out what the pattern to this is. So here's the way I would always lay this out. Now, some of these, and we'll find down the road, they fit a formula. And so if they fit a formula, then it's very easy to get an explicit rule. But they don't all fit those formulas. We only have 2 of them. And if they don't fit the formula, then you just have to figure it out. So here's the way I've always looked at this, is obviously that's the first term, that's the second term, third term, fourth term. For some of the more challenging sequences, and this one is really not that challenging, to be honest with you. You probably figure out the rule for this fairly simply. But they're not all that easy. So I wanted to give you sort of a way that you could look at all of these, especially the harder ones that are tougher to figure out. So what I would say is, so first term, second term, third term, fourth term, we're letting k, and I'll just stick with the letter, we're letting k represent the term number. So what I would say is, okay, then this is k equals 1, this is when k equals 2, this is when k equals 3, this is when k equals 4, right? Because that's my first term, second term, third term, fourth term. So now when I look at that, what I'm saying is, what am I doing to k in order to get this result? Right? It's the same thing that we did up here, is what are we doing to this number in order to get this answer? Well, what did we do? We multiplied it by 3, and then we subtracted 4. And that's what I'm trying to figure out, is what am I doing to k in order to get this result? And I'm looking for a pattern that would describe that for me. So what did I do to 1 to get 1? What did I do to 2 to get 8? What did I do to 3 to get 27? And whatever that answer is, it has to be consistent for all your terms. I can't look at this one and say, well, I multiplied it by 1, because that doesn't work here, right? It's got to be the same answer for all 4 terms. Well, what did we do? Maybe you've already seen the pattern on this. Right? If I raised 1 to the 3rd power, I get 1. 2 to the 3rd power is 8. 3 to the 3rd power is 27. 4 to the 3rd power is 64. So what we did was, we took our k value and raised it to the 3rd power. Right? And so this now is the explicit rule for that sequence. And now I could use that explicit rule to find any term I want. So now if I said, okay, what's the 10th term? Well, 10 to the 3rd power would be the 10th term. So anyway, that's just a good process is looking at this in order to figure out the explicit rule that we get right here. Okay, so here's the difference. Recursive rules. A recursive rule defines the pattern by linking it to the previous term. And that's what a recursive rule is all based on. It's all based on the previous term. I'm always using the previous term to get the next term. Right? So in this one, I don't know why they switch letters, because it's just confusing. That N, that's the same as what it was for K up above. And they switch letters on you. Different books use different letters. It doesn't really matter what the letter is. It's just a variable, right? So whether it's n or k or whatever, it represents a term number. Whenever you see something to the n minus 1, well, if this n represents a term number, if I subtract 1 from it, what would I have? The previous term, right? So when I look at this, what I'm saying is the first term, b sub 1, the first term is the previous term plus 5 more. So whenever I see a little b of n minus 1, sub n minus 1, I always just read that as the previous term and then plus 5. So in order to do that, they have to tell me what the previous term was. So notice I really can't go anywhere with this unless I know what the first term of the sequence was. So somewhere in here we're going to have to be given information like this. So if I were to tell you that the first term is 4, and let me make the adjustment on this guy. So this is really what it should look like to be given to you. That should have said b sub n, not b sub 1. But anyway, as I look at this, again, you need to know at least one of the terms in order to start identifying the next term within the sequence. So now we can say if my first term is 4, well then what's my second term? Well, it's the previous term plus 5. So if my first term was 4, then my next term, my second term, would be 9. Term after that would be 14, right? And so the reason we always interpret this as the previous term, obviously you could plug in actual term numbers for this. So if the first term is 4, I would be saying if I wanted the second term, well, then this would now read as 2 minus 1, right? So if I really plugged in the numbers to see what this would look like, the second term is, and if I simplify this, it becomes b sub 1 plus 5. So in other words, in order to get the second term, I have to do the first term plus 5 in order to get the second term. All right, so same thing if I wanted, say, the third term, that would now become b sub 3 minus 1 plus 5. Right? Well, and what's 3 minus 1? That would be b sub 2. So, in other words, in order to get the third term, I would need the second term plus 5. So these are, the recursive rule is all based on the previous term. So let me just throw in the answers to these guys. So if I add 5 to the first term, I get 9. If I add 5 to the next term, I get 14. And you could keep going on and on with this, but here's the issue, and this is why I don't like the recursive rule, is how do I now find the 20th term? If there's no formula like I had up above, the only way for me to get to the 20th term is to continue down this road until I get to the 20th term, right? And I really don't want to do that. What if they said, what's the 100th term? I definitely don't want to do that. So if I started laying them out this way, and if I really wanted the 20th term, what I would need to do with this is what I did up above. Once I started laying out the terms, like 4, 9, 14, and let me just throw one more in there just to have a fourth term. So I would have to lay out the terms like this, and then I would have to do what I did up above, which was write the explicit rule. Then I could plug in a 20 for k, or n, whatever, to get the 20th term, right? Because I really don't want to keep going down this road to find all of my future terms. So let me go down to, okay, let's just write the recursive rule. So here's my sequence of stuff. We are looking to say that any term is equal to something related to the previous term, right? So whether it's adding something, multiplying something, whatever, we want to know how does each term relate to the previous term. Well, how did we get to 6 from 2? How did we get to 18 from 6? Right? On and on and on. What are we doing to each term to get the next term? Obviously, I'm multiplying by 3 in order to get the next term. So in order to get each term of the sequence, I am multiplying the previous term times 3 in order to get the next term of the sequence, right? And obviously you could test that to see that it works. But that would be the recursive rule for this. Let me move on. All right, let me, but before I show you this, I do want to show you something from page 643. Let me pull that up. So one of the things that we can look at with a sequence is the idea of a converging sequence versus a diverging sequence. And this is where the connection is going to be made to calculus, because you will spend, and we'll actually be doing this towards the end of our year too, is we're going to talk a lot about limits. But it's like one of the huge transition pieces from pre-calc to calc is the idea of a limit. The limit has to do with the value that something is approaching. And we've already talked about limits a little bit in first semester, but that's the main idea, is if these numbers in a sequence are approaching an obvious value, so let me show you what I'm talking about. So here's the sequence. 1 over 1, 1 over 2, 1 over 3, 1 over 4. That's the sequence. So obviously the explicit rule would be 1 over n. So let's just look at 1 over n for a minute. So if I actually graphed 1 over n, or x, same thing. So if I graph 1 over x, so take a look at what this graph looks like. So one thing to notice is, what part of this graph are we supposed to focus on? Well, look at what's going on here. This is where n equals 1, n equals 2, n equals 3, n equals 4. The numbers are getting bigger and bigger and bigger and bigger. In other words, I am looking at the graph as it goes to the right, as it heads towards positive infinity. Well, as this graph, as I move my cursor towards positive infinity, what is the graph approaching? The graph is approaching the x-axis, or in other words, it's approaching 0, right? So what we are looking at is, as I approach infinity, or as my numbers get bigger and bigger and bigger, what is my results approach? My results, my graph, is approaching 0, right? And so that would be the limit of this function right here, or in other words, in terms of a sequence, it is the limit of this sequence. And so that's what we're looking at on this. If it is not approaching a value, a specific value, then we would say the sequence is divergent, right? It diverges as it gets bigger and bigger and bigger. So let me take you back to what we are looking at here so we can do some examples. So 2 keys that helped with that. One was seeing the explicit rule and graphing it, because limits are the easiest to identify within a graph. Okay, and so let's just look at a couple of these guys right here. Now you could do it without a graph. Okay, I could have definitely done the one that I just did without a graph. Let me show you with one very similar to it. Okay, and so here is the sequence, and here would be the explicit rule you can see taking place, right? It's 1 over 2n. So the idea is, as n gets bigger, what does my answers look like? Well, n is on bottom of a fraction. As the denominator of a fraction gets bigger, what happens to the overall value of this number? Well, as a fraction gets bigger, as the denominator gets bigger, the value gets smaller, right? And you could see that so let's just not even graph it for a minute. I just want you to see something for a minute. So as my numbers increase, so if I have 1/2, 1 over 4, 1 over 6, was my pattern, right? 1 over 8, right? If I keep going on this, well, look at the results that I'm getting. They're getting smaller and smaller and smaller and smaller. In other words, as n gets bigger, what is my answers approaching? My answers are approaching 0, right? And so I don't have to look at a graph for this. In a lot of cases, I can look at just the results that I see here and understand that I am approaching 0 as n gets bigger, as n approaches infinity, right? So major concept that will continue to come back up in a big way down the road. So let's practice a few of these. Let me show you a couple more real quick. So guys, as I look at this one, right, let's see if we can identify the explicit rule that goes with this, because that does help. So what would be the rule that we would write for this? When you get a fraction, here's just a hint. Whenever I try to write my own rules for fractions, I completely look at the top as something totally separate as the bottom. So as I look at this, just looking at the bottom numbers, 1, 2, 3, 4, those can just represent n, because that's my first term, second term, third term, fourth term. As I look at the top, this is where I would separate out 11, 12, 13, 14, and I would say, what did I do to 1 to get 11? Because that's my first term. What did I do to 2 to get 12? What did I do to 3 to get 13? Right? And in all cases, I'm taking my value for n, and I'm adding 10. And you could always test that. You could always test that rule to make sure that it fits any one of those given values. But so now here's the idea. So as n gets bigger and bigger and bigger, what is happening to my results? Are they approaching a specific value? So let's look at the graph here together real quick. So n plus 10 over n. There we go. Let me go this way a little. So as x gets bigger, what is my graph approaching? Well, as I move forever to the right, so as I head towards positive infinity, you'll notice my graph is getting closer and closer and closer to 1. Right? Guys, we've looked at this before. Maybe or maybe not in terms of a limit, but we've looked at this before. What do we call the boundary line that our graph approaches? We call it an asymptote, right? And in this case, it was a horizontal asymptote. Well, when we did rational functions in our first semester, how did we identify horizontal asymptotes? We identified them in this case, when you have x on top and x on bottom. You might remember if the top exponent was the same as the bottom exponent, we identified the horizontal asymptote by doing this coefficient divided by this coefficient. Right? We would have said it's 1 divided by 1, which is 1. That's our horizontal asymptote, and therefore that is the limit that this graph is approaching as x approaches infinity. Right? So strong link to some content that we've already covered. Like I said, this is like the idea of a limit is a major bridge from this course into calculus. And so that's why we do a whole chapter on limits at the end of this class. So let me go back to these guys. So let's try a couple. Right? It's good to see if we can identify some of this stuff on our own as well. So we're going to try it, see what we can identify without the graphing calculator first. And then seeing the graph is always a great backup. Let's first take a look at number 2 here. So if we have 5 to the n power. So let's throw a little notation in here as well. So if we look at 5 to the n, so what we would say on this is, what is the limit? So LIM, what is the limit as x approaches infinity? In other words, when we see that, what we're saying is simply x is getting bigger and bigger and bigger, right? So what is the limit as x approaches infinity of 5 to the n? All right, so there's kind of the notation, the way we would look at it. So now we have to determine if there's a limit and what is it. So in this case, if x is getting bigger and bigger and bigger, so if I plug in a 1, a 2, a 3, a 4, a 5, as n gets bigger and bigger and bigger, what is the result? What is the result approaching? Well, in this case, if I keep putting in bigger numbers for n, I'm just going to keep getting larger and larger numbers. So in other words, in this case, we would just be approaching infinity, right? And we could see that if I'll throw it into a quick graph on here. But if we just said 5 to the n power or x power, whatever, right? We already know what that graph is going to look like, right? So as x gets bigger and bigger, in other words, as I go to the right, what is my graph doing? My graph is getting bigger and bigger and bigger. So my graph is approaching infinity. So in this case, really what we're supposed to say on this, if we are approaching infinity, infinity is not really a number. So our graph is not converging on a value, right? This is what we would call divergent, right? So if your graph is approaching infinity, we just say it diverges, right? So there is no limit on this one, right? So the appropriate way to state this then is that it is that the graph diverges. And so that brings you back to this box right here. So that's what this is saying. So first of all, L, the capital letter L, is the common letter used to define a limit, right? So sometimes instead of writing all of this, right, they identify it as a capital L, but that's only when it's converging on a value, right? When it's approaching an asymptote, like a horizontal asymptote, then it's converging. However, if the limit is infinite, like we just got, or if it doesn't exist, then we would just simply say that it diverges. So there is no limit if it's a divergent sequence. So you're looking at these. One of the difference we're seeing on these cases is these are infinite sequences, right? These are sequences that go on and on and on forever. So that's one of the things that separates out these guys and allows them to have a limit versus the ones that we did at the beginning of this lesson where they were finite, right? There was a specific term that it ended on. These aren't the cases where it says ... and it goes on forever, right? Those are infinite cases. We were looking at ones that would actually have a specific end to it. So when we talk about the 20th term or the 100th term, right, whatever represents the final term that we're seeking, right, then it's a finite sequence, and we don't put a limit on that. So these are really more of a focus on the cases that are an infinite sequence, right? The ones that go on and on forever. So if they never actually have an end to them, then the way we look at them is, what is their limit? What is the value that they are approaching as they get larger? Let's try a couple more. Let's look at number 3 here. So again, this is a sequence ... meaning it's just going to go on forever and ever and ever. So our goal is to see if there is a limit to this sequence or if there is a value that it is approaching. I really don't even need to identify an explicit rule for this in order to find it. I would have to identify an explicit rule to graph it. But if I can tell what the limit is without graphing, then that's great too. So what do you notice about the values here as we move to the right? So as I move to the right and my sequence increases, as my sequence approaches infinity, what are the values approaching? Well, 1/5, 1/25, on and on and on. These values are getting smaller and smaller and smaller, right? So in other words, and there's no negatives in here, they're just simply getting smaller. So I can already tell that this is approaching 0, right? So we're going to say, and we're going to prove it on the graph, but just to show you what we're seeing on this. So we're going to say, and I'm going to have to identify a explicit rule for this in order to put it in these kind of terms. So I guess let's just do that first. So if this is where n equals 1, where n equals 2, where n equals 3, you can see that these are powers of 5. So this would be 5 to the first power, 5 to the second power, 5 to the third power, 5 to the fourth, 5 to the fifth. So in other words, we are looking at 1 over 5 to the nth power, right? It's really just the reciprocal function of this guy. But now it's on bottom, so you guys know as the bottom grows, the overall value gets smaller because it's a fraction. So on this one, we're going to say the limit of 1 over 5 to the n as x approaches infinity is 0. So let's prove it. Let's prove it on the calculator. So if I did 1 over 5 to the n, and we graph that, so you'll be able to see on this one, as we move to the right, you can see my graph is approaching the x-axis, right? It's approaching 0 as it goes farther and farther to the right. And even if you look at the table of values on this, look at those numbers, right? They just forever, as my x increases, my y values get closer and closer and closer to a value of 0 as my x increases. So we can certainly see it on the graph. We can certainly see it just as these specific values increase. We're seeing the value that we are approaching in terms of y. All right, let's try another one. But guys, definitely for some of these that can be a little trickier, always helps to look at the graph. So that's something I always encourage you guys to do. Let me just separate off a couple things here so I don't lose track of what I got. Let's take a look at number 4. So let's see if we can identify what these values are approaching, or if they're approaching anything at all. So one thing that makes this one a little tricky is the way they wrote these fractions. If you actually rewrite these with common denominators, you're going to see the pattern a lot more clearly. So if that's 5, 6, I know a value of 1 is 6, 6, and then 7, 6, and then 8, 6, 9, 6. So if we write it that way, it's going to be a lot more clear as to what we have. They all can be written as something over 6. And again, if these are 5, 6, 7, 8, 9, on and on and on, I can see that as a value of n plus 4 would be the pattern for the numerators. So that's our function. So we're going to look to see if there's a limit to this, or what we can say about it. And just think about it logically for a minute before we even look at the graph. As n gets bigger and bigger and bigger, what's going to happen to the overall value of that fraction? It's going to get bigger, right? So this is going to be another case where we're going to see it approaching infinity. And so we're just going to say that it diverges. There's really no limit that we can state for it, right? It's a divergent series or sequence. So let's just say that. But again, you could take a look at the graph. And if you do, again, you're going to see another one of those graphs that just increases like this, like exponential growth over time. How about this guy? So 0.1 to the nth power. So in this one, they're just giving us the rule. We don't have to identify it. They're just stating what it is. So again, think about this one for a minute. If I have 1/10 to the first power, 1/10 to the second power, 1/10 to the third power, right? As that keeps going, right? Obviously, what's taking place? It's another example that looks just like this, right? Where as x or n increases, my overall value is getting smaller and smaller and smaller because my denominator is growing, right? Which is going to give me an overall smaller value. So here's another case where we can say that the limit of 0.1 to the nth power as x approaches infinity is 0. So again, this is a function that as n increases, the value is converging on 0, right? It's approaching 0. I'll take a look at one more with you because this one's just a little tougher to see. So I wanted to remind you guys of a couple rules that we ran into in first semester as we were looking for horizontal asymptotes. With rational functions like this, let me remind you of the couple rules here. When you have a variable on top and bottom, remember if they have the same exponent, like end of the first, then the horizontal asymptote was this coefficient divided by this coefficient. So in other words, in this case, it would be 3 divided by 1. So this graph is going to have a horizontal asymptote of 3. And as you guys have already seen, as it comes to limits, That's what limits approach, is they approach a horizontal asymptote. So if my horizontal asymptote is 3, then I already know that my limit to this graph is 3, because that's what the graph is going to approach as you go to the right. So let me show you something. So 3n over n plus 1. Let me type that in. So I'm expecting this graph, as it goes to the right, to approach a value of 3. And so you can see, as it goes to the right, it is approaching a value of 3. And I can show it to you if I just graphing the horizontal asymptote here. So you can see that blue graph. As the blue graph moves to the right, it is approaching that red line, which is y equals 3, which is our horizontal asymptote. So we know that graph would have a limit as x approaches infinity of positive 3. So how could we have seen that even without looking at a horizontal asymptote? So I want you to think about this logically for a minute. If I started plugging in numbers for n, like let's just say I plugged in a 1, a 2, a 3, a 4, a 5, these numbers are growing at the same rate because they have the same exponent, right? So let's put in a really big number like 1,000. Well, what would this be? It would be 3,000 over 1,001. Well, if you divide that, you're pretty close to a value of 3. Well, what if we put an even bigger number in there, like 1,000,000? Well, then I'd have 3,000,000 over 1,000,001. Well, if I were to divide those, again, I am getting closer and closer to 3. So even with as we put in bigger and bigger numbers into this, it becomes more obvious what the number is that we are approaching as those numbers grow. Let's look at these guys. So what if the top exponent is smaller than the bottom exponent? Well, the rule that we set in the past was, in those scenarios, my horizontal asymptote was 0. Well, let's look at why that would be the case. As n is growing, well, obviously a power of 3 is going to grow at a much faster rate than a power of 2, right? So in other words, as n gets bigger, my denominator becomes larger and larger and larger than my numerator, right? Well, what have we already seen with fractions where the bottom is growing faster than the top? Well, the overall value of that fraction gets smaller and smaller and smaller, right, as the denominator grows. So we would already know that it approaches a value of 0, even if just thinking about it logically like that. So as n gets bigger, I can already see in this case that my denominator is going to grow faster than my numerator, and therefore, as that grows, I know my overall fraction becomes smaller and approaches 0. So that's why the horizontal asymptote on this is 0, right? That's where that rule comes from. We never really looked at it in terms of limits like this, but that's exactly the connection between a horizontal asymptote and a converging limit, right? Is that's what the graph is approaching. They approach that horizontal asymptote, and that's exactly why, right, as we see it in terms of a limit. What about the case where the top one is bigger than the smaller one, or than the bottom one? So just think about it logically for a minute, right? And you can even ignore this one at this point, because we really only need to focus on, as n gets super, super big, the overall effect on this is really going to be dictated by the biggest powers, right? So what's going to happen overall as we put in values for n that are super large, if the top is growing at a faster rate than the bottom is? Well, then our overall value in this case is going to get bigger and bigger and bigger and bigger and bigger. As the top is growing faster than the bottom, the overall value is going to become much bigger. So then what is this graph going to approach as n gets bigger? It would approach infinity, right? So in these terms, that's why in the past, when we said the top exponent was bigger than the bottom one, we said there was no horizontal asymptote. And that's exactly why. It's not converging on a value if it's approaching infinity. And so this is simply a divergent sequence. So keep those rules in mind for a sec. And now look at number 6. What would it be? So if I just look at my n's, right, I can see that these are both n to the first, which means as n gets super big, and these guys grow at the same rate, the overall effect is going to be dictated by this guy on top and this guy on bottom. So that's why we simply divide this coefficient by this coefficient. So if I looked at 10 over -5, we know that would just be -2, and that's our limit. And if you graphed it, that's what you would see, right? You would see a horizontal asymptote at -2, and as you move to the right, your graph is going to approach that line at -2. So you could certainly graph that and take a look. Let's just write that over here. So I'm going to say the limit of my function, and I'm going to cheat a little bit and not rewrite that whole thing. Is -2. All right, so we're saying the limit of our function as x approaches infinity is -2. So in other words, this is a convergent sequence, and it is converging on -2. All right, let's jump down into these guys. So now we're going to talk about defining arithmetic sequences. So here's where we get into some specifics. There are some formulas that we'll take a look at on page 647. But when it comes to defining an arithmetic sequence is simply a sequence where you are adding the same number every time to get the next term in the sequence. So as you look at this one, we know this is an arithmetic sequence because I am adding 3 every time to get the next term in that sequence. Right? So obviously if I continue adding 3, my numbers are going to keep on growing at the same rate. So because you are simply adding a value, these will always be a linear function. So if you ever to like plot these on a graph, you would see them form a line. So that's important. So that means anything that's exponential cannot be arithmetic. So as I look at these guys, they want me to find a couple things. Let's start with the common difference. Common difference is the number that is being added every time to get the next term in the sequence. One way to look at this, because some of these can be tougher than others, right? This is a very easy thing to identify, right? But how would I identify a common difference if it wasn't such an obvious pattern? Well, just think about the phrase common difference, right? What does difference mean? It means subtraction, right? So in other words, if I take any term and subtract the previous term, I get my common difference. And you'll see that's consistent all the way through. 5 minus 2 is the same thing as 2 minus -1. That's the same thing as -1 minus -4, on and on and on. So you can do this with any two terms, consecutive terms, right? So the way I like to write this is a common difference is a of n, which is any term minus the previous term, which would be n minus 1, right? So obviously in this case, it's 3. But I just like this rule as a reminder for some of the tougher cases that are going to be harder to identify. All right, so how do we find the 10th term? Well, there's two ways to do this. I could just extend this pattern out forever until I land on the 10th term. But the problem is that can be a really lengthy process, because what if they said, what's the 50th term? You definitely don't want to go that route, right? That's where we want the formula. So let me show you the formula that we use for this. And this is actually on page 644, so I got to change that in my notes. I'm not sure why I wrote 647. This should be 644. All right, so here's what this is going to look like. Here's the best way to look at this formula. I'm not a huge fan of the way they wrote it, but here it is a little more clear. This is what you want to see. So a of n is going to equal the first term plus n minus 1 times the common difference. Let me write it out for you guys in what I think is maybe a little bit better of a way to see this. So I'm going to say that any term in this sequence is the first term plus n minus 1 times the common difference. So this is the way I would write it out. This is the way I've seen it in other books. I think that's the clearest way to see it. One thing I always try to emphasize on these formulas is the connection between n and a of n, right? So understand that a of n is a value and n is a term number. So if I were to tell you guys that the fifth term, let's just look at this one. 1, 2, 3, 4, 5. What if I said, now let me do it the fourth term. So if I said the fourth term is 2, that means when this is 4, this is 2. Right? So there's always a strong connection between those two items within that formula. And then again, a of 1 represents the first term, d is that common difference. So if I wanted to find the 10th term on this one, you can see the way they plugged in the numbers. So they put -7 in for the first term. If I'm looking for the 10th term, that makes n 10. We already identified the common difference of 3, and here's my value. So now we would say that a of 10, the 10th term, is 20. Right? And so obviously a formula is going to be way more efficient than trying to lay out this entire pattern until you land on the 10th term or the 20th term or the 30th term. Okay. Recursive rule for the nth term. Let's take a look at that. We've done these before already. So remember that the recursive rule is simply the previous term, or what are you doing, I should say, to the previous term in order to get the next term? Well, what did we do? We're just adding 3, right? So we're simply taking the previous term and adding 3 to get the next term. If you remember back at the beginning of this lesson, one of the things we also talked about was you always have to identify at least one value within the sequence in order to write a recursive rule, right? Because I can't say it's the previous term plus 3 without knowing any of the previous terms. You'd never be able to figure anything out, right? So they always identify the beginning value and then write the recursive rule, because you kind of have to see both of those together in order to lay out the sequence. All right, let's go to part D here. So D is asking for the explicit rule. So the explicit rule was, remember, this is the one involving n that could work for any value. So when it comes to writing the explicit rule for this, when we did this at the beginning of the lesson, we said you kind of just had to figure it out, right? We were saying, right, like in cases like this one, right? This was the recursive or the explicit rule, was this one right here. And we didn't use a formula for that. We just kind of figured it out. Well, if it's an arithmetic sequence, you don't have to just figure it out, right? You can use this formula to identify the explicit rule. So they put in the first term, they put in the common difference, and that's it. When you're writing an explicit rules are supposed to apply to any term in the sequence, right? So we leave n as n. And so they put in the first term, they put in the common difference, and this is really the explicit rule, but it is nice to simplify it. So they distribute the 3, combine it with the -7, and it cleans up to be this one. And this is probably a better way to look at it than this one. But again, now that I have the explicit rule, just like I did with the formula right here, I could now use it, right here, I can now use it to find any term in the sequence. So now if I said, what's the 10th term? Well, plug in a 10 for n, and you'll figure out your 10th term. All right, discuss this last one with me, and we're going to cut it off after this one. I was going to go a little farther, but this has taken a long time, so we're going to cut it off after this example. So what about this one? Is that arithmetic? That's a little hard to tell. Of course, I could put those into a calculator, and I would see a common pattern to this. Let me show it to you this way. Remember what we talked about here? If I can take any term and subtract the previous term, and that's consistent all the way through, then I know it's arithmetic. So if I were to say, well, what's the natural log of 9 minus the natural log of 3? What would that come out to be? Well, remember, one of the things we did earlier was combining logs into a single log. So if it's subtraction, we combine them through division. So the way we did this earlier this year was to say, let's combine it to a single log where it's this guy over this guy, which is obviously natural log of 3. Let's see if that's consistent. Well, what if I did that with this one and this one? So if I again said, what's the natural log of 27 minus the natural log of 9. I think you guys are probably seeing this already, but it's going to come out to be the same value, right? Because if I condense that into a single log through division, I have 27 over 9, which is the natural log of 3, right? And you can see that's going to continue to happen. 81 divided by 27 is 3, that over that is 3, that over that is 3. So the way that we set those up through that idea shows us that this is consistent all the way through, right? So my common difference is the natural log of 3. So definitely one that would help to have sort of a formula approach to it, because it's definitely not as obvious. As far as finding the 10th term, use the same formula that we used right here, right? So I'm going to plug in my first term, which is the natural log of 3. If I want the 10th term, I'm going to put a 10 right there. And right here, we're going to put the natural log of 3 as our common difference. Let me flip over and show you that. So they've already laid that out for us, so they put in that information right here. And from there, you're just doing cleanup as much as you can. You do have to use some log rules. So you got to remember some of those log rules in order to be able to condense or combine terms within it. And so they worked it down to this idea right here. I'd say that's probably a better look for it. But anyway, it's just use of a formula. As far as the recursive rule, remember we start by identifying the first term. And then we say, okay, what are we doing to the first term in order to get the next term? Well, we're taking any term and we are adding the natural log of 3 in order to get the next term in the sequence. So that's the recursive rule. And now if you wanted to write the explicit rule, really the exact same thing that we did right here, except instead of putting in a 10 right there, you just leave it as n. Right? And so that's what they did here. Same formula. You leave this as n. And then if possible, it's good to clean things up as much as you can to look like this. So that's really it as far as this lesson. I was going to continue on to this, but I definitely need to save that one for next time. If you want to go through an example with me right now, then stick around and I'll go through this one with you if you need to see one thing further here. So let me go through this concept with you guys. This one's a much more simpler one, kind of like the first one that we did in this idea. So as far as the common difference goes, I can see that if I take any term and subtract the previous term, clearly we are adding 5 every time to get the common difference. So what would the 10th term be? Well, we would say a of 10 is using the formula, first term, plus n minus 1. In this case, it's a 10 because we're finding the 10th term, times the common difference of 5. Right, and so if I just clean that up, so 9 times 5 is 45, plus 31 is going to give me 76 as the 10th term. As far as the recursive rule, remember for the recursive rule, we always want to identify the first term. And then we want to say, so then for as far as the recursive rule goes, we are taking any previous term and we are adding 5 in order to get the next term in the sequence. As far as writing the explicit rule, remember it's the exact same thing that we did right here, only you don't put in a specific number for this. We just leave n as n. So as far as the explicit rule goes, we would say it's my first term plus n minus 1 times the common difference. All right, and so that's the way we would lay it out for writing the explicit rule. So again, it's good to clean this up as much as we can. So distribute the 5. Combine like terms. So if that's 5n minus 5, looks like we will end up with 5n. And again, if that's negative 5 plus 31, I'm going to get 26. And so that would really be the best way to write the explicit rule for this.